Hello, everyone. My name is Katie Emilio, and I'm an engineer in the Professional Development Department at ACI. I'd like to welcome you to today's webinar, Performance Engineered Concrete Mixtures. For continuing education credit, attendance for the entire duration of today's webinar will earn you a certificate of completion for 1 PDH. ACI is an approved education provider for the American Institute of Architects and the International Code Council, and this webinar has been approved for 1 learning unit. This webinar reviews performance engineered concrete mixtures, and you can find the description in your handout, as well as the learning objectives. And now I'd like to introduce our speaker for today. Matthew D'Ambrosia, PhD, PE, is a principal with MJ2 Consulting, PLLC, where he specializes in solving difficult problems for the construction industry. His interests include materials optimization for specialized applications, durability-related mechanisms such as volume change and cracking, as well as new approaches to prediction and verification of service life, durability, and sustainability. He has expertise with large infrastructure and energy projects throughout the U.S., such as bridges, highways, dams, and power plants. He has 18 years of experience in concrete materials behavior and research, including characterization of mechanical properties, development of new experiments, numerical modeling, and mixture optimization. Dr. D'Ambrosia is an active member on many of ACI's committees, including ACI 329 Performance-Based Specifications. He is the current chair of ACI 209C on Model Applicability and Uncertainty, and he is the past chair of Committee 07 Awards for Papers. And now, Matt will begin today's presentation.
Thank you, Katie. I'm very happy to be here today and want to welcome all of you to today's webinar. One of the first things I'd like to do actually is just get an understanding of what type of audience we have. I'd like to throw a survey out there so that all of you can respond and I can get a better idea of who my audience is. So if you wouldn't mind, please indicate what area of industry you're practicing in, and then we'll get the feedback, and hopefully that'll give me some information as to who's in our audience today.
All right, Matt, it looks like we've got about 77%, so I'm going to go ahead and close that for you.
Great. So this is wonderful. We have a very good distribution. About half of us are engineers in practice, and then 20% or so contractors, 20% in the lab world, and about 10% academic. So that's a great distribution. I think that's very helpful for me to move forward and have a better understanding of who I'm speaking with. So thanks everyone for participating. At this time, I'll move forward into the presentation, and what I want to start with is just a brief discussion of what are performance engineered concrete mixtures. And essentially we have historically in the industry, we've relied on prescriptive specifications in many aspects of developing concrete materials. And what we have today, as we move more towards hybrid specifications, we have new types of concretes that we can get into that are where we're actually engineering for certain aspects of performance that go well beyond. In the past, we focused on strength, or we focused on maybe one aspect of durability, and now we're starting to develop more well-rounded specifications. One of the first applications of performance engineered mixtures that I'll talk about is use of an alternative cement for high early strength, calcium aluminate cement, and how we considered the durability, basically the durability function of that material for specific applications in repair. And so I'll spend some time focusing on the repair applications there. And the other application I'd like to spend some time talking about is the new construction side and how bridge deck performance was addressed. All of the work that I'm talking to you about today is work that was done in conjunction with the Illinois Tollway, and it was done while I was at my previous company, CTL Group. The Illinois Tollway has been very innovative in allowing new specifications and in particular incorporating performance testing and performance engineered mixtures. So they've been a strong supporter of this concept, and I'll talk a lot about that as we go through the slides. Under new construction, we're going to look at both performance testing and also some mitigation strategies. So I hope you'll all have an interest in not only how we can monitor this performance, but also some of the methodologies that exist for mitigation of cracking. And then finally, I'll wrap up and cover a few comments that I want to give you on the field experience and how these mixtures have actually done historically so far. It's been about 7 or 8 years now that they've been in use, so we have some good idea now of how well things are going. So moving ahead, the first idea I want to present to you is just the concept of what makes a good performance engineered mixture and a performance specification. And historically, we've always focused on mechanical properties in the engineering world. Specifically for concrete, we're concerned with compressive strength. And there's been a lot of momentum moving away from that in the last decade or so. What really needs to be examined is a good view of the overall performance for performance engineered mixtures. We want to incorporate mechanical properties as well as durability and constructability. And constructability, I think, is the aspect of the overall concept that's generally not given enough attention. What makes a mixture constructible? And in many cases, we're talking about what influences the contractor's ability to place the concrete and not encounter problems with either consolidation or setting or things like finishability. And there are much fewer test methods in that realm. So I really want to emphasize that is a new concept, that incorporating constructability concepts into performance-based mixtures is really important, because I think it adds to the success of the overall project and really makes for a concrete mixture that in the long run has benefit to the owner and has performance that the engineering side really wants. So just as critical in my mind as the mechanical and the durability segments. But under durability, you see I have highlighted cracking there, so that's one of the aspects that I will focus on. And under mechanical properties, I've highlighted elastic modulus. And the reasoning is there's a movement now towards specifying things like elastic modulus instead of compressive strength. And I want to touch on that a little bit and some reasons why that may be good or may not be so good depending on the application. So I think that's important as well. What has driven this work and what I think is critical to the development of a performance-based spec is that we have existing prescriptive specs, and in many states you have DOTs, for example, that utilize standard repair mixtures, and what you'll find is they're often significantly over-designed for strength, mainly because we're focused on early opening strength and trying to ensure that the opening happens within a very tight time frame, which is usually a consideration that affects traffic, it affects safety. We really don't want to take any risks with having an opening be delayed. So on a prescriptive basis, the mixtures are often significantly over-designed because those are really, the focus is really on that early opening. What often comes out of that is then a lack of durability. We have significant cracking issues. So what was done, particularly in the Illinois Tollway, they wanted to identify mixtures that would give us the opening strength that was necessary without having to prescribe the exact mixture, but then also using a few techniques to try to mitigate cracking also give us some long-term durability enhancements. So what was investigated there was a calcium aluminate-based product. Calcium aluminate cement has been around for quite some time. It's actually, it dates back to the 1800s, and so it's not a new product. But what happened in the early part of the 20th century was that it was discovered that this cement had a drawback to it where the strength would diminish over time. And this is a process called conversion. This conversion process meant that if we built structures out of this calcium aluminate cement, it would potentially have a strength diminishing behavior, which could then lead to the risk of collapse over time. And because it was unpredictable and because it was difficult to design for that, calcium aluminate cements were basically not allowed after that for structural applications. But here we're talking about pavement repair and bridge deck repair, and these are applications where the conversion process could be easily accommodated, and the strength loss was not at all significant relative to what was needed from a mechanical standpoint. So that's the first point I want to make. And second, we had a cracking issue that was known to exist in some cases with these cements. And it has a lot to do with the temperature changes that occur at very early ages. So we set out from the very beginning to address this. And one of the things we did was looked at a latex additive. And another strategy we used was to try to mitigate shrinkage with both shrinkage reducing admixtures and pre-wetted lightweight aggregate. And these are both strategies that have gained a lot of attention lately in the last 5 years or so. You'll find numerous references in other ACI documents, and many of your admix suppliers and local concrete producers now have these strategies that they can bring in for a lot of their mixtures. But in this case, it was a highly specialized application. And you can see in the picture on the right-hand side also, we're dealing with mobile concrete mixing, mobile batching systems, and that adds another element to this that can sometimes be a challenge. We have limitations to how many materials we can use. We have limitations to how much of a given material we can carry. So we have to consider some of that before employing the mixture strategy as well. So what is a calcium aluminate cement? Well, these are different chemistries from traditional Portland cements, and that's illustrated here in this ternary phase diagram. I'm sure all of you are thrilled that you got to see a ternary phase diagram today. I know I am. And what we have is the balance between lime, silica, and aluminate. We basically have the CAC system that shifts much more towards the aluminate side, hence the terminology calcium aluminate cement. The raw materials that are utilized in CACs are limestone and alumina bauxite. So we have different raw materials, different cement chemistry, and very different performance with these products. Within about 5-6 hours, you see roughly comparable strengths to 28-day strengths of Portland cement systems. So we're up over the 40 MPa or the 3,500 psi range, which is where we want to be in a lot of cases for pavement repair. What we also see is strengths that go much past that in the short time frame. And over time, you can also see, in this figure, we see over the period of about 1 year that transient high strength is then lost over time and becomes stable out past 1 year. In the alternative configuration, we see in the lower curve on this chart is a large section that hydrates, in which heat builds up in the concrete. And in this case, the conversion process is bypassed. And so we have two different types of behavior that can potentially be seen depending on the temperature history. And that's important in a lot of ways. But when we're talking about concrete repair, we set out to investigate this material, and understanding that strength really wasn't our concern, what was ultimately done here was we investigated these two different types of temperature histories for how they affected durability. And I think that's really the critical thing here, that the durability properties were studied closely, and we wanted to ensure that it wasn't just strength that we were after for that early opening time. So here's some results. What we were seeing in laboratory tests, and this was closely reproduced after we took the material to the field and started employing it in actual construction. We saw very similar strength profiles, but basically we're getting about 4,000 to 6,000 PSI in a few hours. So pretty amazing stuff. The strength takes off. And if you haven't worked with CACs before, they're impressive from that aspect, that you know, really you can get that early strength and then reliably get it. It comes in no matter what your early temperatures are. We found that in a lot of cases, the early temperatures was not as significant. What happened, though, is when we started to add the latex, we began to discover with the latex that it gave us great freeze-thaw durability. As you can see here, we had well over 300 cycles, and the relative damage, the relative dynamic modulus that we were seeing in the sample was very significantly outperformed some of the other materials that we had previously investigated. But we began to see that there was some scaling resistance issue with the material when it was not utilized with the latex. So this is where the latex came in as a significant improvement from the durability side. And then when we examined shrinkage and overall volume change behavior, we didn't really see a whole lot of improvement. So what was interesting here is, you know, we were achieving the durability, as I said, with scaling resistance, but not necessarily the shrinkage resistance that we wanted. So we started to move towards a different type of testing. What we wanted essentially for these patching systems was concrete mixtures that didn't crack. And we began to employ a new test method that it's been around for about 15 years or so now, but some of you may not be aware that it's out there. It's a test called the restrained shrinkage ring test. This is a test that allows us to cast a concrete donut around a steel pipe for restraint. And as the steel pipe pushes back on the concrete as it tries to shrink, you ultimately develop tensile stresses, and you eventually will typically see cracking in most concretes. If this cracking happens within the first week or so, we consider this to be a potential risk from, and in particular with patching materials, we want the cracking to happen sometime after the first week after the sample has been cast. What you can see in this figure is that despite the fact that these mixtures had similar linear drying shrinkage, which is the top chart, the bottom chart tells us that they had vastly different cracking behavior, and to the point where ultimately we want to address this further, because all of the mixtures we looked at were cracking within the first week. So we weren't really satisfied with this behavior. We want to get that cracking time frame out past 1 week before we start to use this material in the field. We did see plenty of improvement in other properties as well. We had, with respect to the chloride penetrability, we saw really with CAC systems in general, vastly superior performance to traditional Portland systems. And then we saw even better performance when we incorporated the latex. So really pretty outstanding results in those cases. But it wasn't until we get to this figure when we started to incorporate another strategy, which was using lightweight aggregates. And these pre-wetted or some say saturated, although they don't really fully saturate. These lightweight aggregates, and these are lightweight fines that are being utilized. These are materials that are becoming very popular. There's some momentum throughout the industry with regards to using these materials for internal curing, even in Portland-based concrete. In this instance, I believe this was the first attempt that anyone's made to look at this material in conjunction with calcium aluminate cement. And we weren't really quite sure what we would see in terms of benefits, but the CAC responds differently as a cement during the hydration process when it has water available. It tends to vastly change the early hydration kinetics. And what we saw was a little bit of a reduction in the speed of early strength gain, but not enough that it really worried us from a field standpoint. But we did see a tremendous improvement in crack resistance. So we had no cracking at all in these rings. They went out past 28 days, which is considered, in the ring test, it's considered essentially the gold standard. But remember, just 2 slides ago, I was showing you that these concrete mixtures without the lightweight material were cracking within about a week or so. So with some addition of saturated lightweight aggregate, we've eliminated cracking in the restraint ring. This is a very significant improvement and something that I heavily emphasize as a strategy that works with this material. As I said, it did throw us off a little bit with respect to the early strength, and that's something that you have to design for, but I believe it can be accommodated. So this is what we ultimately wound up with. It was a hybrid specification. It wasn't purely performance-based. We wound up with using the saturated lightweight and no cracking in the ring test for at least 14 days. That was our target. And then finally, we upped the final cementitious materials content to address some of the sensitivity that we saw with strength. So I think the conjunction, using the latex in conjunction with the CAC allowed us to get the scaling and the freeze-thaw durability, and then using the saturated lightweight for internal curing gave us the crack resistance. So this is I believe, a successful program, and right now we're working on ways to implement it in the field. Some of the comments I have in terms of making the specs successful, you really have to ensure that the producer and the field teams take ownership of the concrete, and that field control is kept very tight on the aggregate moisture and the batching program. The mixtures, as I said, there was some sensitivity to the early strength was somewhat sensitive to the presence of moisture in the aggregate, and also the gradation and the admixture dosages. So there are things that need to be watched for in this material, and as we continue to do further work investigating it in the field, I think that in particular in the Illinois Tollway system, I think that we're going to continue to see improvements there. So moving on to Portland cement patching, this is some work, again, that was done in conjunction with the Illinois Tollway, and they were trying to address the cracks that were occurring with the prescriptive repairs. And what we ventured into in this case was optimized concrete mixtures that, again, utilize the ring shrinkage test so that we can prevent the cementitious content from becoming excessive. Trying to get the strength that we need, but not over-design significantly for that early strength. And some of you may be thinking that, well, you know, doesn't that add a little bit of additional risk in terms of making our strength? And yes, I agree with that. There's some additional things that you need to watch for during the trial batching process. You especially need to make sure that you have your admixture dosages dialed in, and then as the temperatures outside begin to change, that you have that relationship between the early strength and your accelerator dosage, let's say, that you have that figured out so that you're not relying purely on the cement to get your early strength, because I think that's where folks run into trouble with cracking. What we often see with some of these mixtures is, again, the length change testing doesn't really indicate a whole lot of a problem here. I mean, the early age length change is higher than we want it to be. The strengths were nearly double what was needed in some cases with the prescriptive mixes. So no emphasis at all given on durability. And we wanted to get away from that because, again, the ring shrinkage test is available. It allows engineers to develop specifications that prevent cracking problems. So to give you a little bit more feel for this test, again, we said it's this concrete donut. We instrument the inside of the steel pipe with strain gauges, and then we monitor the strains on a computer, and that tells us when the cracks are going to occur. It also allows us to compute and monitor the stresses in the concrete over time and get a rough idea for how quickly the tensile stresses develop. So again, I think this is a critical test that it gives us a lot of insight into what types of concretes are beneficial from a cracking standpoint. This figure illustrates exactly what I'm getting at in terms of tweaking the concrete mixture, because we're trying to promote mixtures with cracking times that are longer. And as you can see on the very left-hand side of the blue line is it's the lowest water cement ratio line or set of data that we have. It's also the highest paste content. As we move towards the right and we go from the blue line to the pink line, we have a slight increase in the water cement ratio and a slight reduction in the paste content. And we continue to see that benefit as we move further and further. What this tells us is what we typically are doing in the industry to promote early strength and higher long-term strength is going in exactly the opposite direction that we want to go with respect to cracking. And there are plenty of situations when strength is most important. And obviously, for construction sequencing, form stripping, moving to the next level in a high-rise structure, your compressive strength is dominating the early behavior, and that's really what you want. But in the cases where I'm discussing today, I'm veering towards the patching and the paving materials and bridge decks. It's not compressive strength that drives us. It should be the cracking behavior, and we need to be able to accommodate that to a greater extent. So this is where this type of mixture design approach, where we can start to promote cracking materials like the very last trend line here that we have in green, and the one farthest to the right. Now we've gotten towards a good compromise. It's a 0.42 water cement ratio, 33% paste. This is a mixture that still gets 4,000 PSI at 24 hours. So it meets the requirements of the tollway patching system. And with a little healthy dose of accelerator, there were never any issues getting the strength in this mixture. So again, instead of relying on the cement to do this job, we're veering more towards accelerator dosage and trying to reduce the amount of cement that's in the system. And we're seeing great benefit from that. So here's where we wound up revising the performance requirements. And this is a purely performance-based specification. We have opening to traffic strength and acceptance for payment strength at 14 days. And these are the two strength criteria that were emphasized. Once you get the opening to traffic strength, really there was no concern regarding getting the later age strength. I don't think we ever had any issue getting that in less than a few days, but you'll notice it's not really required until 14 days. The time to cracking minimum for a patching material in this system is considered 10 days. So we have basically the bare minimum that we need to make a small patch in a deck or a pavement and not see cracks. With respect to freeze-thaw, we have a performance test requirement there, and also for drying shrinkage. And these are more for our long-term durability, so we're trying to emphasize that as well. Chloride penetrability was also specified, but this is also for long-term durability, but it also allows us to get a sense for how the long-term corrosion behavior is going to potentially affect us. And provided you can prevent the cracks from occurring, we can get significantly long life expectancy out of these patching systems. With the type of chloride resistance that we are getting, and in conjunction with mitigation of cracking, we're expecting the life of the patches made under this program to exceed 30, 40 years under the current expectation for tollway salt loading. So really outstanding performance that I believe they're going to be getting over the long run. The other two factors that were assessed carefully, but again, the sense here is that this is a patching system. ASR was also specified, and the air void system. Now, the one point I would mention about the air void system is that can be a great alternative to actually having to run a freeze-thaw test. Freeze-thaw testing is a long-term test that takes about 10 weeks, and I have yet to run into a construction contract where a 10-week time frame is accommodated as part of the mixture development process. It's really a challenge. The pace of typical projects doesn't really allow us to get that testing in. So what we've had to do in many cases is move towards the air void system. That's a test where we're simply cutting the sample open and looking at the hardened, polished sample, and that can be completed in a matter of days. So really more of a sensible way to go. How do we expect the industry to respond to this spec and meet these requirements? Well, I think that shrinkage mitigation is the key, and really a lot of different strategies will work, but the top strategies that I have seen utilized are the shrinkage reducing admixtures and the saturated pre-wetted lightweight aggregate. In addition to that, we're seeing a lot of producers now veering towards optimization of their aggregates and incorporating a mid-size coarse aggregate to try to minimize void space, and utilizing higher percentages of SCM, which we've also seen provide a lot of positive benefit in reducing autogenous shrinkage and helping with the cracking issue. And finally, I'd like to mention a relatively new idea that's out there gaining traction in the industry, which is a superabsorbent polymer that can also be used for internal curing. And this doesn't have as much history in the construction world, but these materials have been around for many, many years. In fact, those of you in the audience that may have kids, this is the material that's in a diaper. So if you have a spare clean diaper laying around at home and you shake the powder out of the middle of it, that's a superabsorbent polymer. We are investigating, and there are other groups as well investigating the use of these polymers in concrete and some of the benefits they provide. So really kind of a cool technology. I'm hoping to be able to talk to you more about that in the future. What do these strategies do for new construction? Well, for a bridge deck, let's say, one of the things we're seeing across the board in minimization of cementitious content and employing shrinkage mitigation, we're seeing characteristic drops in elastic modulus. And if any of you are structural engineers in the audience, this may sound like a bad thing. When the elastic modulus drops, that generally means in structures, that means our deflections are going to be higher. But when we're talking about something like a newly constructed bridge deck, we want our elastic modulus to be lower, because what that tells me is the stresses due to restrained shrinkage are diminished. So this is a good thing. And we think that this is in part due to the mitigation techniques, some of these lightweight aggregates and admixtures might be doing some of this, but it's also optimization of aggregates and using the right amount of cement paste can also have this benefit. So we're seeing this relationship that we think is a potential win from a new construction standpoint. And another point to make is we are still tracking drying shrinkage. The linear drying shrinkage, I think, does have a lot of benefit as a performance parameter for long-term drying cracking or drying shrinkage cracking. But I really do believe, as I said previously, that the ring test is the one that we will see the most benefit in. And so here are the results of ring tests. For new construction, we're seeing the BS curve on the very far left side. That's bridge structure. That's a standard IDOT mixture. And this is a concrete that is prescriptive and is used quite frequently in the industry. And as we move towards the right, the green, the red, the lighter blue, and the purple curves, these are the various shrinkage mitigation strategies that were employed. And we saw, in some cases, outstanding performance in the long run, well past 28 days before any cracks were observed in the cases where shrinkage-reducing admixtures were used. And even in cases where just the saturated lightweight aggregate was employed, we saw outstanding cracking resistance, and in the case of optimization as well. Both of those were situations where only one of the three rings cracked. So we're kind of right on the cusp in that case of the cracks starting to become an issue, but it was out past the 10, 14-day mark. So we were really pretty pleased with that compared to what we saw in the control mix, which was all three rings cracking in right around the 2-week mark. So again, a very significant improvement. How do we incorporate this into specifications, you might ask? This is where the rubber meets the road. We want to write specifications that are constructible, that give the contractor tools to be successful, and employ concrete mixtures that allow the concrete suppliers to be innovative. And one of the first things we did here was incorporated an upper strength limit in the specification. This wasn't a popular idea to start with, but the way that we wrote it, if you look carefully at the equation at the top, the minimum required by design was 4,000. If you submitted a trial in the qualification process, you were getting 6,000 PSI at 14 days. That meant that your allowance for your trial was going to be 6,000 plus 1,500. So that would essentially give you a range when you get out into field and basically practice and actually employing this specification. It meant that you'd have a range of 4,000 to 7,500, and that gave enough wiggle room. And in many cases, we haven't had issues with this, and in many cases, it's been no problem at all. The slump loss was considered as well. This is another constructability issue that was emphasized, and trying to make sure that none of the strategies employed caused a problem on the construction side. The ring test, of course, as I mentioned, was employed with a 28-day minimum to time to cracking. However, we also included an out. So if you have a mixture with less than 600 pounds of cementitious and a minimum dosage of SRA, you didn't have to run that test. So we have had some success with that as well, because there are cases where either the time frame or the testing cost or something about running that test, it's more desirable to perhaps just use the mixture that we are confident in. And so it becomes somewhat prescriptive in that case. We also specify drying shrinkage as well as freeze-thaw. But again, the freeze-thaw test, there's an allowance that if you meet the air void parameters, that test is not required. And as long as the aggregates meet a freeze-thaw durability program performed locally by the DOT. So again, not a lot of issues that came up during these tests, except for maybe the time frame that it took. And so we tried to focus, you look in the right-hand column, we tried to focus on minimizing these timeframes to the point where all of the testing could be completed in a 28-day period. And we think that that was accomplished and so far has been fairly successful in making the testing program work for everyone. Finally, the field performance was considered by the Illinois Tollways to be outstanding. The feedback that I had gotten, and these are results from a few years ago, but essentially the feedback is that not a single crack was found on the newly constructed Jane Addams Tollway, I-90, that goes through Chicago. And further improvements are currently being investigated. We're in the process of finalizing a report where now the life expectancy of the high performance concrete is being pushed out to 75 years from the previous 50-year life. So this involves looking at not only the rapid chloride penetrability test, but also new test methods for resistivity and formation factor. And if those of you that aren't familiar with resistivity and formation factor, if you want to email me, I can send you some information on that. But those are new methods that are quicker and easier to run than the traditional rapid chloride test, but give us basically some of the same information and can be used as well in modeling and prediction of service life. So really some pretty cool trends coming out of that program. Finally, I want to conclude with some discussion of, just overall performance engineered mixture benefits. And the primary benefit to those of you in the audience that are concrete producers, perhaps, this allows you to innovate. It allows you to seek out the strategies that you prefer and which may be the best combination for your materials or perhaps the best cost option for you, but it gives you that freedom to select the approach that works best. It encourages the optimal usage of cementitious material, which again, I think is a big key to durability. And it also encourages uniform gradation or optimization of aggregates, which again is becoming more and more of a trend lately. And I think we're seeing, some of the other folks that are working on this, like Tyler Lay at Oklahoma State, he has the tarantula curve that you may have seen. This is really the direction that I think things are going to go in our industry, that careful selection and utilization of uniformly graded aggregates is the key. And finally, just to conclude, the field performance is showing that these new directions and new strategies are providing the desired improvements. And we're seeing an increase in service life because of how much crack mitigation is being witnessed here. So I'm hoping that you, all of you in the audience, have found some things in the presentation today that'll be helpful for you and maybe get to employ some of this in your own work. If any of you at all have any questions or comments now at this time, I'd like to take those. Thank you very much. I'd also like to acknowledge my co-authors, both Jan Boschelik and Jose Pacheco at CTL, and Bill Vavrick and Dan Gankars at ARA. And finally, last but not least, Steve Gillen of the Illinois Tollway. Thank you very much.
All right, Matt, thanks for covering that material. We do have some questions we'd like to have you address. So the first question is, could you elaborate on the impact of SRAs on freeze-thaw resistance?
That is a wonderful question. Appreciate you asking. SRAs historically, and they've been around for going on 30 years now, really have only been popular in the industry maybe for the last 15, 20 years or so. They began, and then the chemical is a surfactant, so you have to be aware that there is the potential for that chemical to interact with air entraining agents. And very early on, when shrinkage-reducing admixtures were introduced to the industry, we saw significant effects, and some of the products that were out there were causing problems with air entrainment. And so there was some concern over this. But the admixture companies, in my opinion, identified the problem quickly and have addressed it with reformulation over the years. And the products that I find on the market today have significantly less influence on the air entrainment. They do tend to knock down air a bit, so it's likely that your air entrainment dosages are going to have to be increased. But in my opinion, it can be managed, and it's very predictable now. So once you make that adjustment for the presence of the SRA, I think that the performance is much more stable. And more importantly, I would say that a hardened air void analysis, as we've employed throughout these programs, gives us the ability to not just check the plastic air content, but also emphasize what's happened in the final hardened state. And so that preemptively excludes any situations where you might be losing air. Maybe it's unstable after you take the plastic air, it kind of falls out of the system. And we want to, of course, prevent any surprises. So that's why a lot of what I talked about today, we do concentrate on hardened air. We also did run a lot of freeze-thaw performance, and there's a tremendous history with testing, especially with the tollway and all the freeze-thaw tests that have been done over the years. And there was always good correlation between the hardened air void system and the freeze-thaw performance. So I really don't have any concerns as far as that goes. Very good question. I think as long as in practice, as long as you keep an eye on the plastic air content and the hardened air void system, I think you are relatively safe in not having freeze-thaw issues.
Okay, we do have another question. The question is, will shrinkage and cracking be further mitigated if a repair mixture has a specified compressive strength that is similar to the existing concrete?
Not necessarily. The compressive strength compatibility between the substrate and the repair material is not as important as the modulus compatibility. What you really need to match is the modulus of the repair and the modulus of the substrate, and that reduces the potential for concentrated stresses around cracks and joints and anywhere that could be a stress concentration. As I mentioned in the talk, we did focus on the modulus and trying to make sure that it wasn't, we tried to reduce the modulus essentially as we were working. So that probably is why compatibility of strength is mentioned, is because that historically that's how you come up with the modulus. But I would really advocate measuring the modulus directly rather than trying to predict it from the strength, because I see many ways, especially in this program, many of the strategies that we employed can change that relationship between strength and modulus. So you don't want to lose sight of what's really critical, which is the stress development.
Matt, another attendee is curious. This presentation focused on bridge construction and obviously the tollway work. Do you see this direction of this performance engineered concrete occurring in the design of other structures?
That's a wonderful question. I absolutely do. There are many situations where this type of approach, the performance-driven specification, is desirable. The cracking test in particular, if I was coming up with a repair mixture in any type of a structure, whether it's a pre-bagged product or a mixture designed from scratch, I would want to use the ring test as my guide to coming up with a mixture that was not going to be prone to cracking. And if you're repairing a parking deck or any type of a structure, anything that you could imagine, that is a test that will help guide you from the high cementitious traditional repair mixture towards more of a optimized, shrinkage mitigated type of concrete. And you should also be aware that many of the bag products out there are designed with this in mind. And I think some of the pre-bagged product manufacturers, they even advertise as crack-resistant repair concretes. These material developers have already spent some time looking in this ring test method as well. And the best thing you can do if you're either on the construction side or you're on the specifying engineering side, ask for data. Ask your material suppliers if they've run the ring test. And if they can provide you ring test results that show 28 days or more of crack resistance, you're in really good shape, I think, for many structures in having a good crack-resistant material.
Matt, could you speak to some of the successful construction practices for bridge decks, high-performance bridge decks, to achieve some of the no cracking that you mentioned? And this attendee is looking for maybe some direction on placement time, curing methods and timing, et cetera.
Yeah, so there are a lot of important things there. And as I mentioned, we focused on constructability in the performance testing, which gave us mixtures that were not prone. We basically wanted concretes that would not be prone to slump loss. And we examined a time frame of about 45 minutes for that. There are admixtures out in the industry today. The hydration stabilizers would be the class of materials that I would encourage you to investigate. These hydration stabilizers can increase that time frame even further. And then there are slump retention products as well. And the slump retention products, in conjunction with hydration stabilizers, can give you mixtures that have better time frame for placement than you may have. Some of you may have bad experiences in the past with high performance concrete. It can be sticky. It can be difficult to place. It can be, losing slump very quickly. And that's where the admixture side of things needs to come into play. So if you're talking about a different application from, say, a bridge deck, you may want to extend that slump life requirement to the point where, you can require much longer slump life. And I've seen this done quite often for things like drilled shafts and difficult mass concrete placements as well. But if you are doing bridge decks, I think the current strategy that we've used with about a 45-minute time frame for slump loss, that seems to work quite well. As far as curing goes, most of the successful projects that I see are still employing a 7-day wet cure. And I think one of the critical steps to that is making sure that your curing water is not producing any kind of a temperature shock. I've even seen in some cases, and especially with mass concrete, you could get away from moist curing and provide water retention curing instead, where you're curing simply with a plastic sheet and then potentially following up with a curing compound after the sheet is removed. What you really want to avoid is shocking the surface of the concrete, especially when it's in higher temperature during hydration. You don't want to shock the surface with cold water. And I think that's a mistake that can sometimes be made when we have wet curing programs. So I'd watch out for that one. So I think that addresses curing. I'm in favor of wet curing as long as it's done carefully and the water is not significantly colder than the concrete surface. And then I also favor moisture retention and curing compound strategy. So those are good benefits that will help in the long run.
Matt, you had mentioned super absorbent polymer admixtures, and this question is regarding that. What are your thoughts on the use of super absorbent polymer admixtures, do you think, with regards to shrinkage mitigation versus some traditional shrinkage mitigation methods? And where do you think that might go in the future? Do you think different water to cement ratios may affect the performance when using those admixtures?
So to answer the first part of the question, I think that super absorbent polymers are effective at mitigating shrinkage. I think that they may hold a lot of potential benefits in addition to that. Some of those benefits may come along from just the continuing hydration process. And having these polymers in the system, I believe, is also going to provide some benefit in the long run for some of the other things that I mentioned, like reducing the modulus. I think that that's a benefit in accommodating crack mitigation strategies. The question about the water cement ratio and how that impacts things, I think that the water cement ratio with the superabsorbent polymers, you have to be careful to not include the water that's being soaked in by the polymer. And in that case, the water cement ratio that you're looking at should just be of the paste by itself. And I think that, a little bit lower water cement ratio may be desirable because you may want to compensate a little bit for the voids that are coming in along with the polymer. But this may not be necessary because I think the polymer systems can be optimized, and the size and the distribution of the polymer will have a lot of impact on things like strength too. So it depends on what product you're looking at. There are many different polymers out there, and the chemistry of the polymer, and as I said, the size and the distribution of it will all have a significant influence on the final properties. So I do think the technology is very promising. I think that it'll be coming along soon, within the next years or so, that we're going to start to see these products hit the market, and they may be really beneficial for some other things as well. I mean, you could have instead of a internal curing strategy, you could have a super absorbent polymer that reduces slump. So if I'm a contractor and I have a truck on site that I'm having to reject because the slump is a little bit too high, we all know that the slump, is being slightly high is probably not a big risk these days for quality, because so much of our strength is dependent on admixtures anyway. But if you had a product that could be introduced on site and maybe tighten the slump up a few inches, I think superabsorbent polymers can do that. And then you might have a product that you could employ to save you from having to reject a truck. So there's a totally different application there, but it's a neat idea that I think has some promise.
Matt, we have one final question for you today. Mm-hmm. In terms of the owner on a job, how does the owner benefit from a performance versus prescriptive specifications?
So that's a good question. The owner, I believe, benefits in several ways. First, it allows them to incorporate new and innovative materials and shed some of the risk of trying to design all these new materials themselves, because they're really emphasizing the performance, and the testing all has to be done on the particular mix during the qualification process. So you have more confidence then in that particular concrete mixture, because the testing has been completed recently, as opposed to selecting a prescriptive mix off the shelf, and maybe materials have changed over time and you don't necessarily know what the current set of materials is doing because the testing hasn't been done. So I think that there's a lot of benefit in better understanding how the mixtures will perform. And of course, the performance that we're getting out of these mixtures in terms of crack mitigation, that's a benefit to the owner. You get longer life expectancy, service life increase. You get benefits to long-term performance, even on some of the other things we talked about, like freeze thaw and scaling benefits. So these are test methods that we, on a prescriptive mix, you wouldn't even be running these tests. So you really don't know, for your conventional concrete mixtures, you don't know that you have this performance to begin with. So that's where I think having a performance-based spec and actually running these tests on new and innovative materials, it will open the door to better performance in many projects, and it allows you to dial in and optimize the performance for your needs. There are also other ways that performance specs can be beneficial for sustainability. You can specify on a performance basis, you can specify that higher SEM contents be part of the spec, and this can be a strategy. And then you essentially can also direct the entire program to help minimize costs. So if you're giving contractors and ready-mix producers the freedom to be flexible and choose which strategy works best for them, then I think the hope in the long run is that the whole program ultimately results in the lower cost to the owner, because you can also create competition that these products are being utilized. And does the supplier want to use an SRA, or do they want to use saturated lightweight? And if they get to pick based on what's available to them and based on cost, then ultimately that's a benefit to the whole industry.
Great. Matt, thank you so much for taking some time this afternoon to speak with us and share your expertise with our attendees. Also, if you are looking for continuing education credit and were unable to join us for the duration, please be sure to complete the online quiz at aciuniversity.com. Some of the topics for our upcoming live webinars are shown on your screen and in your handout. That does conclude today's webinar presentations, and we hope you will choose to join us for future learning opportunities.